Hello everyone. So in this video we are going to solve trapping rainwater. So we are given n non-negative integers representing an elevation map where the width of each bar is 1. Now we have to compute how much water it can trap after raining. So in example 1, the width of each bar is 1 as mentioned in the description, and the height of each map is given as an input map. Okay. So we'll solve this question using two approaches. So let's just see first approach. So let's start with the first index. So at this index, if you want to know how much water is trapped here, so let's say if some water comes here, will it be able to collect here? No, because there is no bar to the left of it that can hold this water. So the water that will be collected at this bit is 0. Okay. Now at this position, there is no way to collect the water because to the left of this bar, there is no bar that can hold the water. Okay, so the total water collected here is also 0. Now at this position, we know that there is a bar to the left of it and there is a bar to the right of it. Okay, so if any water that comes here will be collected between these two bars, and the amount of water that is collected here depends on the smallest bar. So to the left of this bar there is a bar that is largest, and toward the right of it there is a largest bar, that is this bar. Okay, so between these two bar, which one is smallest? So this is the smallest bar, and the amount of water collected is minimum height bar, that is this bar, that is 1, minus the height of the bar we are standing at, that is 0, multiply the width of the bar, that is 1, is 1. So 1 unit of water is collected here. Now at this position, the maximum height bar toward the left is this bar, and the maximum height bar toward the right is this. Now amount of water that can be collected at this position is 0, because if any water came at this position, the water will flow toward the left or toward the right. So the water won't stay at this position. So amount of water collected is 0 at those position. Now let's say at this position. Okay, so at this position, the maximum height bar toward the left is this bar, and the maximum height bar toward the right is this bar. Okay, so how much water will be collected at this position? So we'll take the minimum height bar, so that is this bar. Okay, that is 2 height minus the height of the bar we are standing at, that is 1, multiply the width of the bar we are standing at, that is 1, will give us 1 unit of water. So this water is 1 unit of water, and this is also 1 unit of water. Now we are at this position. At this position, the maximum height bar toward the left is this bar, and toward the right is this bar. Now this water will be found using the minimum height bar. So minimum height bar is this one. Okay, that is 2, minus the height of the bar we are standing at, that is 0, multiply the width of the bar we are on is also 1. So total 2 units of water is collected here. Okay, now at this position, the maximum height bar toward the left is this one, and the maximum height bar toward the right is this one, and the amount of water collected is minimum of the left height bar. Okay, that is 2, minus the height of the bar we are standing at, that is 1, multiply the width, that is 1. So this water is 1 unit. At this position, the maximum height bar is this one, and there is no maximum height bar toward the right except itself. Okay, so water won't stay at this position. Okay, so if any water comes here, the water either flows toward the left or toward the right. So the water collected here will be 0. At this position, the maximum height bar toward the left is this, and the maximum height bar toward the right is this, or you can say itself. Okay, so how much water will be collected? So the minimum height is this or this. Okay, that is 2, minus the height we are standing at, 2, multiply the width of itself, that is 0. So at this position, if any water comes, it will flow toward the right side, it won't stay at this position. Now at this position, the maximum height bar toward the left is this, and the maximum height bar toward the right is this. So the amount of water collected is minimum height bar, so that is 2 minus the height of the bar we are standing on 1, multiply the width of the bar is 1 unit. So this is 1 unit of water that is collected. Now at this position, the maximum height bar toward the left is this one, and to the right is itself only. So there is no maximum height bar, so itself is the maximum height bar toward the right. Now there will be no water collected at this position, because if any water that comes here will either flow toward the left or will flow toward the right. So the water collected here is 0, or by mathematically we can see that minimum height bar, that is to itself, minus the height of the bar we are standing at, multiply the width, will be 0. Now at this position, the maximum height bar toward the left is this, and toward the right is itself, okay, or none we can consider. So if we consider none, there is no bar toward the right, then it will be minimum will be 0 minus the height of bar we are standing at, that is 1, multiply 1, it will be negative, okay. Or if we say that this bar itself is the maximum height bar toward the right, then in that case it will be 1 minus 1 multiply 1 is 0. So when we were calculating the amount of water that can be stored at this position, we can say that at this position, let's say at this position, the maximum height bar toward the left can be 0, because there is, sorry, toward the left is this one, okay, the maximum height bar toward the left is this one, and toward the right is this. But for this position we can say that the maximum height bar toward the left is 0 or itself, and the maximum toward the right is this one. Okay, when we say that the maximum toward the left is 0, then at this position minimum is 0 minus the height 1 multiply the width will give us negative result, so which we will not count. But if we say at this position this bar itself is the highest bar, then in that case 1 is the height of minimum bar minus the height of itself, width will give us 0 units of water. Similarly, at this case, for example, at this case, the maximum height bar toward the right. So if we say that the maximum height bar toward the right is this bar, then the amount of water will be collected is, that is, height of that minimum bar is 1 minus the height of itself, that is 2, multiply 1 will give us negative result, which we will not count. But we can also say that at this position the maximum height bar toward the right is, you can say, itself only. So when we say itself, then it will be 2 minus 2 into 1, which will be 0, okay. So for example, at this position we can say that the maximum height bar toward the right is either this one or itself. In that case the result will be same. So for example, at this position the maximum height bar toward the right is left is this one, okay, or itself. When we say this one and this one, the minimum is either this or this or this, anyone. So that is 2 minus the height of bar itself, that is 3, it will be negative, okay. So we will not consider this result. And when we say the bar itself is the maximum height bar toward the left and the right, then it will be 3 minus 3 multiply 1, that is 0. So at every position, if we know the maximum height bar toward the left considering the index at which we are itself, or not considering it, and the maximum height bar toward the right, then we will be able to know how much water will be collected at that position. Okay, so let's just recap what we did. So at any position, if we know what is the largest length bar toward the left and what is the largest length bar toward the right, okay, let's say in this solution we will not consider the index itself, okay, we will not consider the height of index at which we are standing, we will consider only the left and the right. So at this position the maximum height bar toward the left is this one, and toward the right will be 0. At this position the maximum height bar toward the left will be 0 and toward the right will be this one, okay. So we will not consider index itself. At this position the maximum height bar toward the left is 0 and toward the right is this one, so we will not consider the index itself, let's say. So at this position the maximum height bar toward the left is this and toward the right is this one or this one. Now, if we know these values at each index, we will be able to collect the water. So for example, at this position, we know that maximum toward the left is this and maximum toward the right is this. So we will take the minimum height bar, that is this one, that is 2, minus the height of bar we are standing on, that is 0, multiply the width of bar we are standing on, will give us 2 units of water. So this is 2 units of water. Similarly, for each index, we will be able to collect it. Okay, so let's code this solution. Okay, so length will be height, size, and we'll create two vector. Lmax, the maximum toward the left, so that will be initially all zeros, and Rmax, that will also initially be 0. Now we'll fill this. We'll start with 1, then length and I plus plus, because Lmax at 0th position will be 0, and Rmax for the last index is also 0, right? So we'll start with 1. In that case, Lmax at I for the, let's say, first index will be maximum of Lmax of I minus 1, or the height of this index, that is I minus 1, height of I minus 1. So we are not considering the current index. So we want to know the Lmax for this current index. So Lmax for this current index will be Lmax that we have already created in the previous, okay, or the previous height, okay, might be the maximum height up until now. So we are just collecting the maximum height found until this index. So that will be the Lmax. Also Rmax for this I position will be maximum of Rmax of length minus I, okay, or height of length minus I. So Rmax is the maximum height found until now, until the current index, but from the right side, okay, and Lmax is maximum height bar found until now but from the left side. So we have filled Lmax and Rmax. Now we will calculate the maximum water. So maximum water will be 0 for int I is 0, I is less than length, and I plus plus will take the minimum height bar. So minimum of Lmax at I at this position, what is the minimum height bar toward the left? Sorry, what is the maximum height bar toward the left, and what is the maximum height bar toward the right? And we'll take minimum of that. And if that minimum height bar has height greater than the current height. So if we have a minimum height bar toward, let's say, left side or let's say right side, any of these, we have Lmax at I and Rmax at I, and we will take minimum of that. And if that minimum is greater than the height we are standing on, then only we can collect water. Because if minimum height bar that we have chosen is less than the height we are standing on, then the water will either flow to the left side or to the right side. So the condition is, if the minimum height bar that we have chosen has height greater than the height we are standing on, then we will be able to collect the water. So maximum water that we can collect is equal to the minimum height minus the height we are standing on, multiply the width, that is 1. And finally we'll return the maximum water that we have collected. Let's see if this works or not. So our solution got rejected. So let's just see why. So we initialize length, Lmax and Rmax are 0. Then Lmax at I will be maximum of Lmax at I minus 1 and height I minus 1, that's correct. Okay, so Rmax we have to fill from the right side, not from the left side. So Lmax minus 1 minus I. So Lmax will start filling from the left hand side and Rmax will start filling from the right hand side. So Lmax at ith index will give us the maximum height bar toward the left. Rmax at the current index will give us the maximum height bar found until now from the right hand side. Okay, so our initial test case has been passed and now we will submit this. Okay, now let's just see one more thing. So I told you that if we are standing at ith index, we'll see only the maximum height bar toward the left and maximum height bar toward the right without considering the index itself. Now let's just consider the index itself also. If length is less than or equal to 0, we'll return 0 only. Okay. Now here you say that Lmax of 0th index will be equal to height of 0th index, and Lmax of length minus 1 will be height of length minus 1, right? Now from 1, the Lmax at I is Lmax of the previous position or height of this current index. Similarly, Rmax of the last second position, we'll start with last second because at the last position we have given the Rmax of the last position as the height of the last bar. Okay, now from last second position, Rmax of last position or the height of the last position, and we will remove this I minus 1, the position we are at. So now we are considering the Lmax and Rmax for the current index also. So if we are standing at a bar and if there is no maximum bar toward the left, then the bar itself will be the maximum toward the left, and if there is no bar maximum toward the right, then the bar itself will be maximum at that index. Okay, in that case we don't have to check this because the minimum height will always be greater than or equal to the height we are standing at, right? So we can safely do this. In that case, if the heights are same, this will give 0. Okay, so let's see. Okay, so our initial test case has been passed and now we will submit this. Okay, so our solution got accepted. Now in this case we have created two extra arrays, that is Lmax and Rmax. Okay, and then we initialize this Lmax and Rmax, and for each index, if we know Lmax and Rmax, we will be able to collect the water. But this solution requires an extra space of big O of n, right? And we don't want that. So the next solution will solve this problem without using these two extra Lmax and Rmax. So the next approach will be in big O of n without having an extra space. Okay, so let's see that. Okay, so let's just say that there are many bars here. Okay, what we did in the current solution, so we want to collect water at this position. Okay, now how much water will be collected at this position? So let's say there is a largest bar toward the left and the largest bar is at this position, maybe of any height. Okay, then we have largest bar toward the right side, let's say its height is this. Okay, and these are all smaller than these two. Okay, so the largest bar toward the left is this and largest bar toward the right is this at any position. Now these two bars will fill the water. Okay, so at this position, this is the amount of water that we can collect. So this is the amount of water, and how we will calculate this? So we'll take the minimum height bar toward the left and right. So this is the minimum height, let's say 2 height. Okay, and this is, let's say, 3, and we are standing at this position. So 2 is the minimum height minus the height we are standing. So the height will be 0, multiply this width. Okay, that is 1, that will be 2 units. So this is 2 units of water that we can collect. Now we will use the concept to solve this using the second approach. Okay, so in the previous solution, we used two extra arrays, that is Lmax and Rmax. But at one position, if we know that Lmax and Rmax, why do we need the Lmax array and Rmax array? So for example, if we know Lmax and Rmax here, only two variables, then we'll not need the array. Okay, so for that, we will use two extra variables. So we'll initialize I here and j here. So let's say Lmax initially will be what? So in this case we will use the index itself. So Lmax, so we are standing at I position. Okay, so at I position, what is Lmax? So initially Lmax is 0 here. What is Rmax? So we are standing at last position, so Rmax will give us j. Okay, so Rmax here is 1. Now, where should we collect the water? At ith position or jth position? So in the previous solution, we did that optimization that we will include the LMX and RMX for the current index also. Okay. So in that case, for example, if we were standing at this position, or let's say at this position. So at this position, what is LMAX? So LMAX, there is no maximum toward the left. So we said that, okay, this bar itself is the left maximum. Okay. And what is RMAX? So RMAX is this. So we said this in the previous solution. Okay. We are standing at this. So this is the maximum toward the left and this is the maximum toward the right. We said that. Okay. And we collected water at this position. So now the situation is we are at I and J. We are at I and J. And at I, the Lmax is this, and at J, Rmax is this. So where should we collect the water? Okay, so we'll collect the water on the minimum height bar. So we are at this position. So we'll collect the water at I. So to collect the water at I, you should know Lmax and Rmax, but we know Lmax and Rmax. So at this position, Lmax is 0 and Rmax is 1. So this is Rmax for this position. Okay. So water collected will be 0 at this position. And after collecting the water, we will move Lmax toward the right side. Okay. So I was here. Now I will be at this position. And we will update Lmax. So Lmax will be 1 here. Now at this position, both Lmax and Rmax are same. So where should we collect the water? So let's just say when the both are same, we will collect the water at Rmax side. So we'll collect the water at J. So at J, the left maximum is 1. The right maximum is also 1. So 1 minus 1 is 0. So we'll collect 0 water and we'll decrement J. So J is now at this position. Okay. And our Rmax will be 2 now. Now at this position, Lmax is smaller than Rmax. So we'll collect water at ith position. So at ith position, we have Lmax as 1 and Rmax as 2. So amount of water will be Lmax minus the height we are standing on, that is 1 minus 1 multiply 1, that is 0. So 0 amount of water will be collected and we will move forward. So Lmax will still be same. Okay, so maximum, so left maximum, that will be 1 only. So here at this position, Lmax is smaller than Rmax. So we'll collect water at I only. So at ith position, at this position, the minimum height bar is 1, that is Lmax, minus the height we are standing on, multiply the width is 1. So 1 unit of water will be collected and we will move forward. Now the maximum height toward the left or itself will be 2. Now both are same. So when both are same, we will collect water at jth position. So at this jth position, the minimum height bar is 2 minus the height itself multiply width is 0. So 0 unit of water is collected and we will reduce J. So J is now at this position. So Rmax will stay same, that is 2. Now still Lmax and Rmax are same. So we'll collect water at J only. So at J, minimum height bar is 2 minus the height we are standing at multiply width is 1. So 1 unit of water is collected and we'll decrement J. At this position also Rmax will stay same. So amount of water is 2 minus 2 multiply 1, that is 0. So 0 unit of water is collected and we'll move toward the left. At this position Rmax will update it to 3. Now we will collect water at Lmax side, that is I. So at this position the minimum height bar is 2 minus the height we are standing on multiply 1 is 0. So here 0 unit of water is collected and we will move forward. At this position, our Lmax is 2, Rmax is 3. We will collect water at I only. So here, the minimum height bar is 2, that is Lmax, minus the height we are standing on 1, multiply width is 1. So 1 unit of water is collected and we will move toward the right hand side. Now still Lmax will remain same, Rmax will same, Lmax is smaller than Rmax, so we'll collect water at Lmax, that is at ith index. So at ith index, the maximum height bars are 2 and 3 and minimum of that is 2 minus the height of bar we are standing at is 0 multiply the width will be 2. So 2 units of water is collected at this position and will move toward the right hand side. At this position also, we'll collect water at ith position because Lmax is smaller than Rmax. The minimum height bar is 2 minus the height we are standing on is 1, multiply the width is 1. So 1 unit of water is collected. Now we'll move forward. So I is at this position, and since I and j are equal here, we'll come out of the loop. Okay. So we'll run this loop only when I is less than j. So we'll start with I here and j here. So at each position, we were able to know what is Lmax and Rmax, okay, but not necessarily the largest bar. So for example, at this position, the Lmax was something and Rmax was, I think, this. So Rmax was not this, but this. Okay, so now let's see one doubt. So the doubt is that we want to collect water at this position. We want to collect water at this position. But since we start with I and j, so let's say I traveled all the way up until here and j was able to reach at here only. So this is j and this is I. And in this case, let's say I is able to reach at this position and j traveled all the way up until here. Now, what about this position? Why are we getting correct result? So let's see why. If Lmax is Rmax, we'll collect at j and then I plus plus, else j and then j minus minus. So if we are collecting water here, the condition is that Lmax is less than Rmax. So we found some L toward the left or itself, we found some L that is less than R. Then we will collect water at this position. Okay. So we stopped here because at this position we have Lmax that is less than Rmax. So we have this Lmax is less than Rmax. So we found some R that is greater than this L. So this is L, this is R. Now you are saying that there can be some pillar that is way bigger than this. Why do we care? Because at this position, we are collecting water at ith position. We have some Lmax and we have Rmax that is greater than this pillar. So if rain comes, we know that we traveled all the way up until this point, and this is the largest pillar we found toward the left hand side. So water level will be only up until this point. Okay, water will fill only this point, and we found a larger pillar than this one. So this is the amount of water that we will collect. Why do we care about this largest pillar here if it exists or does not exist? Okay, so we will get the correct answer here because we have Lmax and Rmax that is greater than Lmax. Okay. Now in second case, we are collecting water at jth position. So L is less than R, we'll collect water. Else L is greater than equal to R, we'll collect at j and j minus minus. We are collecting at j, which means that Lmax we found is greater than equal to R. So let's say we found R here, some point. Okay. We traveled all the way up until here. So we found this R maximum. And we traveled I up until this, and traveling all the way up until this we found a Lmax that is greater than or equal to this. So we found either this or we found a greater Lmax. So now you say at this position you might find some larger pillar. Who cares? Because if rain comes, we traveled all the way up until this position, this is the level of the rain. Okay, we won't be able to collect this water because this is the maximum we found until now, and this one. So this is the level of the rain and this is the amount of water that we will collect, right? Okay, so now let's code this solution. So we don't need these Lmax and Rmax. We don't need these. So it will be Lmax will be 0, Rmax will be 0. Max water will be same, and we'll run the loop for while I is less than j, and I will be 0, j is length minus 1. Now at this position, we will update Lmax and Rmax. So Lmax will be maximum of what? Lmax we already have, or height at this position. Rmax will be maximum of Rmax we already have, or height at jth position. So we know Lmax and Rmax at this position. Now if Lmax is less than Rmax, so we'll collect water at ith position. So max water will be equal to Lmax minus height at ith position multiply the width and I plus plus. We collected the water at ith position and now we will move forward. Now max water will be Rmax minus height of J multiply the width. We collected water here and now we'll move backward. And finally we'll return the max water. So let's see. So our initial test case has been passed and now we will submit this. And our solution got accepted. So just to recap, what we did is we, instead of creating two vector arrays for Lmax and Rmax, we created two variable Lmax and Rmax. Now while we'll start with 0 until length minus 1. So we will update Lmax and Rmax. Okay. So at current position we have Lmax and at current position we have Rmax. So if Lmax is less than Rmax, which means we have to collect water at the ith position, else at the jth position, and finally we will return max water.